Hi, we are Team My Heart is in the Vacation, and my name is Jing. Today we are going to present our project, Improving Large Language Models for Multi-Hop Question Answering in RAG, an empirical study. Large language models like impulse retrieval augmented generation have become very popular these days because they could help to mitigate the problem of hallucination by only retrieving the knowledge from an external source and generating response based on this during the inference time. Although RAG systems have been very powerful in many tasks, current RAG systems still struggle with multi-hop question answering, which requires the system to retrieve multiple relevant documents and perform multi-hop reasoning to generate the answer. In the meanwhile, prompt engineering has become very popular since the rise of the large language models, and it has even become a career. Therefore, we are interested in exploring the potential of the prompt engineering to assist the RAG system in addressing the multi-hop question answering and also how it compares to the fine-tuning. I'm going to divide the related work into three parts. The first part is about the multi-hop question answering in RAG. For difficult questions, the large language model usually needs to perform multi-step reasoning in order to answer them. However, this is still a major challenge for the large language model because they will be confused during the inference process. Many researchers have been working to solve this problem. For example, some have focused on designing dynamic interactive retrieval framework based on tree, while others have proposed a new framework to assist the large language model in removing the distracting information. In this project, we want to focus on how prompt engineering can influence a large language model in multi-step reasoning, because we believe that prompt engineering is a very cost-effective method for everyone who wants to create their own large language model for a specific task. We are also interested in the difference between the prompt engineering and fine-tuning, which is another common strategy for teaching the model a new ability. Based on this motivation, we aim to create a RAG system to test how different kinds of prompting strategies and fine-tuning will affect the system performance, and also understand what is the best strategy to enhance the RAG system's performance, and hopefully could gain some useful insights from the communities. We will mainly focus on two key strategies. The first one is the prompt engineering. We are planning to experiment with 4 different prompt techniques. These techniques are designed to integrate with few-shot learning methods. We want to optimize how our system process and respond to the retrieved information. The second one is the fine-tuning. Our focus here is to determine whether the fine-tuning the large language model could help to further optimize the performance of the system, and also whether it could help to improve the model's understanding of the complex prompting strategies. I'm going to divide the related work into 3 parts. The first part is about the multi-hop question answering in RAG. For difficult questions, the large language model usually needs to perform multi-step reasoning in order to answer them. However, this is still a major challenge for the large language model because they will be confused during the inference process. Many researchers have been working to solve this problem. For example, some have focused on designing dynamic interactive retrieval framework based on tree, while others have proposed a new framework to assist the large language model in removing the distracting information. In this project, we want to focus on how prompt engineering can influence a large language model in multi-step reasoning, because we believe that prompt engineering is a very cost-effective method for everyone who wants to create their own large language model for a specific task. We are also interested in the difference between the prompt engineering and fine-tuning, which is another common strategy for teaching the model a new ability. The second one I want to talk about is the prompt engineering. So first I want to talk about the types of prompting. So this prompting strategy has been proved to be a very effective tool for helping the large language models with many areas, such as the common sense reasoning and also symbolic reasoning. The main idea here is quite simple. It guides the large language model to think and solve the question step by step. However, whether it could help the model with multi-hop question answering in RAG context is still remain uncertain, because it requires the model to reason based on different documents and also need to have the ability to distinguish the distracting documents. The next one I want to talk about is the few-shot learning. The concept of the few-shot learning was introduced in the GPT-3 paper. which states that the GPT-3 is capable for achieving competitive performance compared to the previous state-of-art fine-tuning approach by only requiring a few examples to help the model quickly adapt it to a new task. However, the paper also highlights that the GPT-3 is struggle with some future context learning in some aspects, for example, in some certain reading comprehension dataset. The last one I want to talk about is the evidence to generate, the E2G framework. It was just recently proposed. It is designed to enhance the inference ability of the large language model within the RAG system. It includes two steps. The A step requires the model to infer an extra relevant context, while the G step involves passing the evidence to the model for a second round of inference. Since the paper has not made their code public, we believe it will be very useful for the community by re-implement it and also test and compare its performance. So the final part I want to talk about is the fine-tuning. So fine-tuning is a very powerful strategy for helping a large language model adapt it to a downstream task. One of the approaches commonly used is the instruction tuning. It is designed to mitigate the mismatch between the training objective and the user objective, which can lead the model not to follow the user instruction accurately. Instruction tuning is very efficient and also could enable the large language model to respond according to the prompt and the input, which could help the model quickly adapt it to a new task.
Let's dive into the specifics of our methodology, beginning with our dataset and evaluation metric. In our experiment, because we only have limited computational resources, we randomly sample 1,000 data from HotPOT destructor sets as our training data, and then combine all of them as our knowledge source. We also sample 100 data for later use in fine-tuning. For the evaluation metric in our experiments, we selected two metrics to evaluate our system performance. One is the exact match score, which measures whether the model output matches the ground truth answer exactly. Another one is the F1 score, which evaluates how many of the generated words can be found in the ground truth. Let's move on to our approach to prompting engineering. Start with the default prompts. This method uses minimal instruction. It simply asks the system to provide a short and direct answer based on the given context. Next, we have the chain of thought or COT prompts. This simply guides the system to reason step by step about the answer to a question based on the context, resulting in a concise answer that improves logic and comprehension. Moving to EGT templates. EGT consists of two steps. The E step guides the system in locating and referencing specific evidence from context that can answer the question and explain it. The G step takes the evidence and explanation provided by E step as the context to generate the final answer to the question. Lastly, we have the E2G Pro prompts. This prompt technique combines the strengths of COT as well as E2G by first using COT to allow the system to think step by step and summarize the evidence in the context that can be used to answer the question in the E step. Next, let me introduce zero-shot and few-shot learning used in our project. Starting with zero-shot learning, in this approach, we provide the model with no previous examples. It relies entirely on its pre-trained knowledge to understand and respond to the prompts. Moving on to few-shot learning, this method provides the model with three selected examples. Each example includes both a question and the idea answer, illustrating the desired relationship between input and output. This helps the model learn not just the content but also the context of how to correctly respond.
This part is about methodology of RAG system with different large language models. In order to test the performance of the strategy we discussed, we designed and developed a RAG system. We have a retriever that utilizes the BM25 algorithm for similarity search. When a user asks for a question, the system retrieves the top three documents, combines them with a prompt, and inputs these into the large language model to generate an answer. For the large language model used in the RAG system, we want to select one that is open source and closed source model as a representative in our system. For the open source model, we have experimented with Llama 2 7b, Octopus v2-2b, and T5. Llama 2 is a powerful open source large language model developed by Meta, and it stands out as one of the most robust and effective models in the open source community, offering enhanced capabilities for processing and understanding natural language. In order to utilize Llama 2, we use SageMaker Jumpstart on AWS to deploy the 7 billion parameter version for conducting our experiments. During our initial experiment, we found that Llama 2 is very suitable for the RAG context. It is able to follow our simple instructions and generate answers based on them. Octopus v2, developed by Nexa AI, is a sophisticated open-source language model specifically designed for function calling. It introduced a unique function token strategy to enhance both training and inference, distinguishing it from traditional retriever augmented generation methods. The 2 billion parameter version, Octopus v2-2b, is celebrated for its speed and precision, outperforming the Llama 7b plus RAG solution in function call accuracy by 31%. For deployment, we utilize the Hugging Face Transformers library to access the pre-trained model. However, our experiments indicate that while Octopus v2-2b excels in basic tasks, its performance in more complex inference tasks does not meet our expectations. The T5 large model, developed by Google AI and implemented via Hugging Face Transformers as well, is designed to handle a broad spectrum of language tasks by converting them into a unified text-to-text format. This simplification aids in tasks like translation, summarization, and question answering. However, with its 738 billion parameters, T5 Large often extracts relevant snippets from text rather than generating new content, particularly in context logic reasoning scenarios. The GPT 3.5 Turbo model, a closed-source large language model developed by OpenAI, enhanced the GPT series with improved capabilities and efficiency. It builds on the transformer architecture, optimizing for reduced computational demands and quicker response times. With billions of parameters, it adeptly handles a wide range of tasks, from conversational AI to complex problem solving. For deployment, the GPT 3.5 Turbo is readily available through OpenAI's API, facilitating easy integration into various applications and services. In our experiments, we discovered that the GPT 3.5 Turbo model maintains a high level of accuracy in answering complex reasoning questions, even without undergoing fine-tuning. This demonstrates the model's robust pre-training, enabling it to effectively handle intricate tasks right out of the box. This part is about methodology for fine-tuning. After our initial experiments with 2 models without fine-tuning, which we will discuss further later, we found that both GPT 3.5 and Llama 2 struggle with complex prompts. Initially, we want to use different prompt instructions to tune the model accordingly, but due to limited resources, that would not allow us to conduct multiple fine-tunings and experiments. We decided to focus only on tuning the LLM's ability in chain-of-thought reasoning. Our fine-tuning includes 2 steps. The first step is to sample 100 pieces of data from the training dataset. Then we create a fine-tuning data generation pipeline that provides 2 distracting documents and 2 golden documents, along with a question and answer to GPT-4 Turbo through the OpenAI API, and we prompt the model to generate a chain-of-thought reasoning based on it. After finishing this step, we fine-tune the dataset which includes the question, the context with 8 distracting documents, and 2 golden documents, and the chain of thought reasoning based on the question and context, along with the answer. The second step involves using our fine-tuning dataset to fine-tune our two models. For Llama 2, we use AWS SageMaker Jumpstart to conduct instruction tuning. The prompt used in the fine-tuning is similar to our chain of thought template. We tune the model for 5 epochs, with a learning rate of 1A4 and a batch size of 2. We also set the maximum length to 512, because during our experiments, we found that if the max length is too large, the model will start generating nonsense. At the end of the training, the average training loss was 1.45, and the average evaluation loss was 1.38. For the GPT 3.5 Turbo, we conducted the fine-tuning using the OpenAI API to set up a fine-tuning job. The prompts employed were consistent with those used for the Llama 2 model. We adjusted the model's temperature to 0.7 and set the number of epochs to 3, while opting for default values for the learning rate and batch size. Upon completion of the fine-tuning process, the final training loss of the model was significantly reduced to 0.3476, indicating a substantial improvement in the model's performance.
Let's move on to the experiment result evaluation on GPT 3.5 Turbo and Llama 2.7b, both without fine-tuning. For the complexity of the prompt templates, both models show no performance improvement or even worse after using more complex prompt templates. One of the main reasons for this is that the models have not been fine-tuned cannot understand complex prompt well. In addition, although we instructed the model to think in Chen in the COT and E2G Pro prompt template, the model did not really learn and end up just following our thinking process template, which led to negative results instead. In terms of model performance, Few-shot improves more significantly for simple prompting templates, such as the default template. However, for relatively complex prompt templates, such as COT E2G, E2G Pro, it is less effective or even reduces the model performance significantly. The reason is that the few-shot could complicate the prompt template, which make it more difficult for the model to understand the already complex prompt template. In addition, few-shot can work well to standardize the formatting without have to give detailed formatting rules in the prompt. The model can already learn the output formatting in the example very well. In our model comparison, GPT 3.5 outperformed Llama 2 as expected because GPT 3.5 has a significantly larger number of parameters than Llama 2 7b. However, the trend in the effect of different prompting techniques on the performance of the two models is generally similar. For the future direction of the project, we can consider using one-shot learning to standardize the model output without making the prompt template too complicated for the model to understand. In addition, we can fine-tune the model so that it can better understand the prompt template.
Now let's take a look at the result of the fine-tuning. We have conducted fine-tuning on both Llama 2 and GPT 3.5, but the performance of Llama 2 is worse, and it still generates some nonsense during the generation. We think it might be due to that we don't have enough number of epochs, and also we don't have the enough fine-tuning data. However, because we don't have enough research to fine-tune it again, we only run the experiment on the fine-tuned GPT 3.5 and then conducted the analysis based on it. So based on our result and the analysis with the model without fine-tuning, we decided to try using the fine-tuning to help the model understand the prompt and therefore improving its reasoning ability. Here are our results for the GPT 3.5 after fine-tuning. The system performance has improved in all testing scenarios, except for the one with the default future setting, which did not show a very significant improvement. This is likely because the version without fine-tuning already performed well and reached its upper limit. Both TrainSoft E2G and E2G Pro have shown a very significant improvement. I think it's because our fine-tuning, which we target at improving the model's ability in the chain of thought reasoning, has helped this model to improve the ability to understand some complex prompt and also follow the instruction. Although the default template has still achieved the best performance, we believe that using more fine-tuning data with a large number of epochs in the fine-tuning process would be significantly help to improve the model's performance with complex prompt templates. And we also believe that the complex prompt template will help the model to achieve a better performance compared to the default one.